Understanding transformer current relationships is crucial for accurate electrical system analysis. When dealing with a transformer, particularly in scenarios with multiple loads, it's essential to verify the consistency of current calculations across the primary and secondary sides. In this case, we have a 7200 volt primary transformer with a secondary that supplies 120 volts and 240 volt loads. The problem highlights a potential discrepancy between the calculated line currents and the total secondary current. The calculated current in line 2 is 85.75 amps. The presented solution suggests that the total current flowing in the secondary is 81.25 amps. However, this is not logically possible. The total secondary current must be equal to or greater than the current in any individual line. Here's why. The secondary current is the vector sum of the currents in all the lines. Since line 2 has a current of 85.75 amps, the total secondary current must be at least that value or higher. The difference arises from the nature of parallel circuits and the fact that individual line currents contribute to the overall secondary current. Let's break down the calculations to understand where the potential error might stem from. Firstly, we need to determine the current drawn by each individual load. For the 120 volt loads on line 1, we have one load with 15 ohms of resistance. Using Ohm's law, current equals voltage divided by resistance, so the current for this load is 120 volts divided by 15 ohms, which equals 8 amps. The second 120 volt load on line 1 pulls 10 amps directly, as stated in the problem. Therefore, the total current in line 1 is the sum of these two currents, 8 amps plus 10 amps, which equals 18 amps. Now let's analyze the 120 volt loads on line 2. The first load pulls 12 amps. The second load has 8 ohms of resistance. Using Ohm's law again, the current for this load is 120 volts divided by 8 ohms, which equals 15 amps. Therefore, the total current in line 2 is the sum of these two currents, 12 amps plus 15 amps, which equals 27 amps. These values differ from what the question stated. It is important to check the source information. The 240 volt loads are calculated differently. The first 240 volt load uses 9,600 watts of power. Using the power formula, power equals voltage times current, we can find the current by dividing power by voltage. So, the current is 9,600 watts divided by 240 volts, which equals 40 amps. The second 240 volt load uses 4,500 watts of power. Using the same formula, the current is 4,500 watts divided by 240 volts, which equals 18.75 amps. The total current for the 240 volt loads is 40 amps plus 18.75 amps, which equals 58.75 amps. Since the 240 volt loads are connected across both lines of the secondary, this current is shared between the two lines. Each line contributes equally, so each line carries half of the total 240 volt load current. Therefore, each line carries 58.75 amps divided by 2, which equals 29.375 amps. To find the total current in line 1, we add the 120 volt load current to the line 1 contribution from the 240 volt loads. This is 18 amps plus 29.375 amps, which equals 47.375 amps. To find the total current in line 2, we add the 120 volt load current to the line 2 contribution from the 240 volt loads. This is 27 amps plus 29.375 amps, which equals 56.375 amps. Therefore, the total secondary current would need to be the vector sum of 47.375 amps and 56.375 amps. However, we can approximate the total secondary current as the arithmetic sum in this case, giving us 103.75 amps. Because 103.75 is greater than 85.75 amps, this makes more sense. The key concept here is that the total secondary current is determined by all the loads connected to the secondary winding. The total secondary current will always be greater than or equal to the largest individual line current. Now, let's address the possible causes of the discrepancy in the provided answers. Firstly, there may be an error in the book's calculation for the total secondary current. It is not uncommon for errors to occur in textbooks or solution manuals. Secondly, there may be a misunderstanding of how the 240-volt loads contribute to the line currents. As explained above, the 240-volt loads draw current from both lines, and this must be accounted for when calculating the total line currents. Thirdly, there could be an issue with the provided values for the loads. For example, if one of the resistance values is incorrect, this would affect the calculated current for that load and consequently the total line currents. In conclusion, the statement that the total secondary current is 81.25 amps while the current in line 2 is 85.75 amps is incorrect. The total secondary current must be at least 85.75 amps or higher. If the currents in the individual lines are significantly different, this indicates that the transformer is not evenly loaded. In a balanced three-phase system, the currents in all three lines should be approximately equal. However, in a single-phase system, some imbalance is expected. It is important to note that these calculations assume an ideal transformer, meaning that there are no losses in the transformer itself. In a real-world transformer, there will be some losses due to factors such as comagnetization and winding resistance. These losses will result in a slight difference between the input power and the output power, and consequently, between the primary current and the secondary current. However, these losses are typically small and can often be neglected in basic calculations. It is always important to double-check your work and to use common sense when evaluating the results. If something does not seem right, it is worth investigating further to identify the cause of the discrepancy.